Hello there, and welcome to the Sleepy Science Channel. Tonight, we are exploring the magical world of magnets. These simple objects may seem ordinary, yet the forces inside them reach far beyond our everyday world. Magnetism shapes our planet. It guides animals across oceans. It powers trains that float above rails and machines that can look deep inside the human body. All of it comes from an invisible force that surrounds us every moment of our lives. You cannot see magnetism with your eyes. You cannot taste it or hear it. Yet it flows through Earth itself and stretches far out into space. It bends light from the sun. It steers charged particles through the sky. It hides inside rocks that formed billions of years ago. And it quietly powers much of the technology that keeps the modern world moving. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do. Let your shoulders soften and allow your breathing to slow. And allow your mind to gently unwind as we explore the invisible world of magnets together. Let's begin. Earth is a giant magnet, and your compass proves it. Deep beneath your feet, far below the crust and mantle, a restless ocean of liquid iron is turning, swirling, and churning around Earth's solid inner core. That motion creates electric currents, and those currents generate the planetary magnetic field that wraps around the world. A compass needle aligns with that field, which is why such a small object can reveal something so enormous. In a sense, every compass is whispering news from the center of the planet. This invisible shield does more than guide travelers. It also helps protect the surface from charged particles streaming in from space. Without it, Earth would be a harsher and more exposed place. So when a compass quietly points north, it is not performing a tiny trick on a tabletop. It is responding to a force that reaches from the deep interior of the planet, far out into space. Every magnet you touch is ruled by invisible fields. A magnet is never only the solid piece you can hold in your hand. Around it stretches a region of influence where forces act across empty space, shaping the motion of metal objects, compass needles, and electric charges. That unseen region is called a magnetic field, and it is the real reason magnets feel so uncanny. You move the magnet, and something nearby answers without strings, gears, or contact. Iron filings reveal these hidden patterns beautifully. Scatter them near a bar magnet, and they swing into curved lines that trace the field's structure. The pattern is strongest near the ends, where the pull feels more intense. This is why a small object can seem almost alive when it jumps across a gap toward a magnet. What you are witnessing is not simple attraction in the ordinary sense. You are seeing space around the magnet organized into a map of force, with every point giving matter its marching orders. Cut a magnet in half, and both halves still have poles. This surprises people because it feels like cutting a battery in half and expecting one piece to keep only the positive end while the other keeps only the negative. Magnets do not work that way. Slice one into two smaller pieces, and each piece forms its own north and south pole. Cut those again, and the pattern repeats. The reason lies inside the material itself. Countless tiny regions are aligned in the same direction, so the whole object acts as a magnet. Breaking it apart does not peel north away from south. It simply creates smaller magnets from the original ordered structure. That is one reason magnetism feels so strange. It refuses to behave like many other things we know. Even after centuries of study, scientists still have not found an isolated magnetic pole in nature. Every ordinary magnet seems to insist on arriving as a complete pair, no matter how many times you try to divide it. Some of the strongest magnets on Earth can lift cars. In scrapyards and factories, magnetism stops feeling like a classroom curiosity and starts looking almost unreal. Massive industrial electromagnets can hoist wrecked cars into the air as if they were toys, holding tons of metal with no hooks, chains, or visible grip. The effect is dramatic because the force seems to appear from nowhere. Yet the secret is straightforward. When electric current flows through coils of wire, it creates a magnetic field. Build the system on a large enough scale, feed it enough power, and that field becomes strong enough to seize heavy steel objects in an instant. Then, with a switch, the current can be cut and the load released. That controllability is what makes electromagnets so useful. Cranes can sort scrap rapidly, move dangerous material from a distance, and do work that would otherwise require slower and riskier handling. It is hard not to feel amazed when invisible force becomes strong enough to rearrange a landscape of metal. Birds can sense Earth's magnetism and use it to navigate. For migratory birds, the sky is not empty. It is filled with clues that human senses cannot detect. Many species travel extraordinary distances across continents and oceans, often with stunning accuracy, and evidence suggests that Earth's magnetic field is one of the guides they use. Some birds seem able to detect direction from the field itself, giving them a kind of built-in compass that works alongside the sun, the stars, landmarks, and smell. Researchers have explored whether special chemistry in the eye may play a role, or whether tiny magnetic particles in the body help convert the field into biological information. The full story is still being investigated, which makes it even more fascinating. Somewhere inside a bird's living tissues, physics and biology appear to meet in a way that lets the planet's invisible field become useful knowledge. A robin crossing night skies may be doing something that still feels close to magic, even under scientific light. Magnetism helps power cities, hospitals, trains, and the internet. It is easy to think of magnets as small objects that stick to doors or pin notes to a fridge. In reality, modern civilization leans on magnetism constantly. Electric generators at power stations use rotating magnetic fields to produce the current that lights homes and runs businesses. Motors in pumps, fans, trains, and factory machines turn electrical energy back into motion. In hospitals, magnetic technology helps doctors see inside the body. In data centers and communication systems, magnetic components help manage power and signal flow. Even the infrastructure behind the internet depends on equipment shaped by electromagnetic principles. That is what makes the subject so astonishing. This invisible force is not tucked away in laboratories alone. It is woven into ordinary life at every scale, from giant systems that keep cities alive to hidden devices inside everyday machines. The world feels digital and modern on the surface, yet much of its motion still depends on one of nature's oldest and strangest forces. Lightning can leave magnetism frozen inside ancient rocks. When certain rocks cool from a molten state, magnetic minerals within them can align with the surrounding field and lock that direction into place. In some cases, a lightning strike can also jolt material so intensely that it leaves behind a magnetic signature. This means stone can act like a record keeper. Long after the original event is gone, the rock may still preserve a trace of the magnetic conditions that shaped it. Geophysicists read these signatures to investigate ancient landscapes, past field directions, and events that vanished millions or even billions of years ago. It is a remarkable idea that a flash lasting a fraction of a second, or a cooling process buried in deep time, can be stored in matter for ages beyond human memory. A rock on a shelf can therefore hold a history far stranger than its plain surface suggests, carrying evidence of vanished storms and ancient planetary conditions within its mineral grains. Your brain can be studied using magnetic fields without surgery. One of the most extraordinary uses of magnetism is that it allows scientists and doctors to investigate the living brain while the skull remains closed and untouched. In magnetic resonance imaging, powerful fields and radio waves interact with atoms inside the body, especially hydrogen in water, to produce detailed pictures of soft tissue. That means the brain can be viewed with remarkable clarity, helping reveal tumors, injuries, strokes, and subtle structural changes. Other magnetic techniques can even probe brain activity more directly, tracking signals linked to thought and sensation. What makes this so astonishing is the contrast between the delicacy of the organ and the scale of the physics involved. The same force that can move steel in a scrapyard can also help map the folds and structures of the mind. Magnetism becomes a bridge between the invisible machinery of matter and the hidden workings of consciousness, opening windows into ourselves without a single incision. Horseshoe magnets were designed to concentrate force at their tips. The horseshoe magnet is one of the most iconic shapes in science, and its form is not just for show. By bending the magnet so that its two poles sit close together, the design channels much of the magnetic field into the gap between the tips. That makes the pole there noticeably stronger and more focused than it would be if the poles were spread far apart. It is a wonderfully practical piece of engineering. Rather than creating more magnetic material, the shape simply guides the field into a tighter working region. For students, that made the horseshoe magnet a memorable classroom object. For engineers, the same idea showed how shape could improve performance without changing the basic material. What makes it fascinating is how visible the principle becomes. A bent bar suddenly behaves with greater purpose. The magnet seems to gather itself, bringing its invisible force forward and concentrating it where work is most likely to happen. The sun can hurl magnetic storms powerful enough to hit Earth. The sun is not only a blazing ball of hot gas, it is also a colossal magnetic machine. Its magnetic field twists, knots, and snaps as the solar surface roils and boils. When that tension releases, the sun can launch huge bursts of charged particles and plasma into space. If one of those outbursts is aimed our way, Earth can be struck by a geomagnetic storm days later. Then the effects begin to ripple outward through modern life. Satellites can be disturbed. Radio communication can falter. Power systems can come under strain. High above the poles, the sky may answer with brilliant auroras as incoming particles funnel into the upper atmosphere. The astonishing part is scale. Events on a star more than 90 million miles away can shake technology on our world. Magnetism makes that connection possible, linking Earth and Sun across the emptiness of space in a relationship both beautiful and dangerous. A magnet can push, pull, spin, and levitate objects. Most people first learn that magnets attract certain metals, but that is only the beginning of the story. Depending on the setup, magnetic forces can also repel, causing objects to push away from each other. Arrange fields carefully, and they can create rotation, which is the principle behind electric motors. Shape conditions in more specialized ways, and magnetism can even hold something above a surface, apparently defeating gravity. That is the principle behind magnetic levitation, where powerful systems can support and guide moving vehicles with very little physical contact. Scientists have even used intense fields to levitate small living creatures and droplets of water. The deeper wonder is how versatile the force becomes once engineers learn to direct it. It is not limited to a single dramatic trick. It can grip, release, accelerate, suspend, and stabilize. Few natural forces move so easily from a child's first science lesson to some of the most advanced technologies humans have ever built. Lodestones are natural magnets, formed deep inside the Earth. Long before people learned how to build magnets in workshops and factories, nature had already made a few of its own. Lodestones are pieces of magnetite that became magnetized through geological processes, often involving powerful natural fields and ancient heating events deep within the planet. They are rare, which adds to their mystery. Imagine finding a dark stone that can tug at iron without any visible mechanism. To ancient observers, that must have seemed almost supernatural. Yet lodestones gave humanity one of its earliest encounters with magnetism in its raw, uncultivated form. They were not polished tools or deliberate inventions. They were strange gifts from the Earth itself. In a way, they are magnetic fossils from a hidden world of heat, pressure, and mineral change. A lodestone makes the story of magnetism feel older and wilder, because it reminds us that the planet was performing this invisible trick long before anyone knew how to name it. Ancient people were using magnetic minerals long before modern science. Magnetism entered human life before there were laboratories, equations, or formal theories to explain it. Ancient people noticed that certain stones could attract iron, and that discovery was remarkable enough to be remembered, traded, and discussed across cultures. What began as curiosity slowly became usefulness. Magnetic minerals were handled as wonders, but they also opened the door to practical tools that would eventually reshape navigation. This is one of the most enchanting parts of the story. Human beings met magnetism first through direct experience. A stone pulled metal, and that was enough to spark questions. Why should rock reach across space at all? Why should one object answer another without touch? Those questions belong not only to scientists, but to anyone who has ever been startled by the hidden behavior of the world. The earliest encounters with magnetic minerals remind us that science often begins in astonishment, with an ordinary hand picking up an extraordinary stone. The word magnet comes from an ancient Greek place name. The language of science often carries old journeys inside it, and magnetism is no exception. The word magnet is thought to trace back to Magnesia, a region in the ancient Greek world associated with magnetic stones. That small linguistic detail gives the subject a lovely sense of depth. A word we use for an invisible force in phones, hospitals, and power systems may have roots in a place where people simply noticed unusual minerals in the ground. It is a reminder that scientific vocabulary is not always born in abstract thought. Sometimes it begins in landscape, trade, and local wonder. A region lends its name to a stone, the stone lends its name to a phenomenon, and the phenomenon eventually helps describe part of the structure of the universe. There is something beautiful in that chain. A place on Earth left its mark on human language, and that language now travels wherever people speak about one of nature's most powerful and mysterious forces. China used magnetic compasses centuries before Europe did. One of the most world-changing uses of magnetism emerged in China, where magnetic compasses were developed and used centuries before they became established in Europe. Early forms were sometimes made from lodestone or magnetized needles, and they transformed a strange natural force into reliable direction. That shift mattered enormously. Once magnetism became a navigational tool, it changed what was possible on land and sea. Clouds could hide the sun. Coastlines could vanish into darkness. Familiar landmarks could disappear. Yet a magnetic compass still offered guidance. The effect on trade, travel, exploration, and empire was profound. What makes this history so compelling is that it turns an invisible planetary field into a human companion. A person standing on a deck in uncertain weather could hold a small instrument and gain orientation from the Earth itself. That is a breathtaking partnership between nature and ingenuity, and it began far earlier than many people realize when they first hear the story. Earth's magnetic field is born in its liquid outer core. The source of Earth's magnetism lies in a place no human being will ever visit. Thousands of miles below the surface, beyond the crust and mantle, the outer core is made largely of liquid iron and nickel, moving under immense heat and pressure. That flowing metal conducts electricity, and as the planet rotates and the fluid circulates, those electric currents generate the magnetic field. This process is called the geodynamo, and it is one of the grand hidden engines of our world. The astonishing part is that a force affecting compasses, satellites, and auroras begins in a realm of darkness and pressure far beyond direct reach. We know it through physics, seismic evidence, and the behavior of the field itself. So every time a compass turns or charged particles are deflected high above the atmosphere, the cause traces back to motion in a buried metallic potion. Earth is not magnetized by accident. It is actively making magnetism from within. The magnetic North Pole does not stay in one place. Many people imagine the magnetic North Pole as a fixed target stamped onto the top of the planet. In reality, it wanders. Its position shifts over time because the flowing metal inside Earth's outer core is always changing, and the field changes with it. That means the magnetic map of the planet is alive rather than still. For navigators and scientists, this movement matters. Charts must be updated. Instruments must be corrected. Airfields can even need runway numbers changed when magnetic directions drift enough. There is something deeply fascinating in the fact that north, at least magnetic north, is not a permanent destination. It roams across the Arctic in response to processes happening far below the surface. A child learning to trust a compass may imagine a steady and eternal guide, yet the guide itself is moving. That gives magnetism a wonderfully restless character. Even one of the oldest tools for finding direction depends on a target that refuses to remain perfectly still. Earth's magnetic poles have flipped many times before. At long intervals in the planet's history, the magnetic field has done something that sounds almost impossible. North and south have traded places. These reversals are recorded in rocks, especially in volcanic material and seafloor crust, that preserved the field direction when they formed. The process does not happen in a dramatic instant like a switch being thrown. It unfolds over long spans of time, and the field can weaken and become more complex along the way. Still, the idea is astonishing. The directional framework that compasses rely on has reversed again and again across deep time. If humans had been around during one of those transitions, the magnetic world would have slowly reorganized around them. This tells us something profound about Earth. The planet's magnetism is not a permanent stamp. It is a living system with a history of upheaval. Even the global field that seems so steady today belongs to a much longer story of planetary change and reversal. Some rocks preserve a record of vanished magnetic worlds. Certain rocks act like tiny time capsules. When minerals rich in iron cool or settle into place, they can lock in a signature of the magnetic field that existed at that moment. Scientists call this remanent magnetism, and it allows ancient stone to preserve evidence from worlds that no longer exist. A continent may have drifted elsewhere. A field direction may have changed completely. A region may even have belonged to another hemisphere in a distant age. Yet the rock still carries a magnetic memory of where and how it formed. That is extraordinary, because it means geology is not only about what we can see in layers and fossils. It is also about invisible traces hidden inside mineral grains. A plain rock can therefore become a witness to lost planetary arrangements. In its magnetic record sits information about past latitudes, shifting crust, and ancient field behavior, all preserved silently until someone learns how to ask the right questions. The seafloor carries magnetic stripes like a planetary barcode. Far beneath the waves, the ocean floor holds one of the most elegant pieces of evidence in all of Earth science. As molten rock rises at mid-ocean ridges and cools into new crust, magnetic minerals inside it align with the planet's field and lock that direction in place. Because the field has reversed many times, the newly formed crust preserves alternating bands of normal and reversed magnetism. These bands spread outward on both sides of the ridge in matching patterns. When scientists mapped them, the result looked like a barcode running across the seafloor. It was a stunning discovery because the symmetry was too clear to ignore. The ocean floor was recording its own creation in magnetic ink. That pattern revealed not only the history of magnetic reversals, but also the process by which new crust forms and moves apart. Few scientific clues are so beautiful. Invisible force became visible pattern, and the planet's hidden behavior suddenly stood plain for human eyes to read. Magnetism helped scientists prove that continents really do drift. For a long time, the idea that continents move seemed too bold to accept. The shapes of coastlines hinted at it, and fossils suggested ancient connections. But many scientists wanted stronger proof. Magnetism helped provide it. Rocks on different continents preserved magnetic directions that only made sense if those land masses had once been joined and later shifted apart. The matching magnetic stripes on the seafloor made the case even stronger by showing that ocean crust was being created and pushed outward over time. This turned continental drift from a controversial suggestion into a convincing physical story. What makes this so satisfying is that the evidence came from something no one can see directly. Not mountains, not rivers, not obvious fractures, but hidden magnetic signatures locked in stone. An invisible force helped reveal the motion of entire continents. It is one of science's most dramatic moments, where magnetism became a witness and the planet's slow dance finally gave up its secret. A compass points north because Earth surrounds us with magnetism. A compass works because its needle is itself a tiny magnet, free to turn until it lines up with the magnetic field that surrounds the planet. That sounds simple, but the idea is extraordinary. A small object in your hand is responding to something that stretches across mountains, oceans, deserts, and ice. No batteries are required. No map is built inside it. It works because Earth provides the signal. That is why compasses became such trusted companions for travelers, sailors, surveyors, and explorers. In fog, darkness, or empty landscape, the needle still offers direction. It does not care whether a person is standing in a forest path or on an open sea. It is listening to the same planetary force in both places. There is something deeply beautiful about that. The world itself becomes part of the instrument. A compass is not merely a tool you carry. It is a conversation between a human hand and the invisible structure of the Earth. True north and magnetic north are not the same. This distinction has shaped navigation for centuries, and it still surprises people when they first hear it. True north is the direction of the geographic North Pole, the point where Earth's axis of rotation meets the surface. Magnetic north is the direction a compass needle points, which depends on the magnetic field and its shifting geometry. The angle between them is called magnetic declination, and it changes from place to place across the world. In one location, the difference may be small. In another, it can be large enough to send a traveler seriously off course if ignored. That means a compass is not a perfect translator of geography on its own. It gives magnetic direction, and the user must understand the local difference. There is something wonderfully subtle in that. Even one of humanity's most trusted tools comes with a hidden correction. The needle points faithfully, yet the planet asks you to know a little more before you can truly trust the path. Near the poles, compasses can behave in surprisingly strange ways. As you move closer to the magnetic poles, a compass stops acting with the tidy confidence people expect. The field lines there plunge more steeply into the earth, so the needle is pulled not only sideways but downward as well. The normal compass is designed mainly to turn horizontally, which means the balance can become awkward and unstable in high latitudes. It may drag, tilt, or wobble instead of giving a crisp direction. Explorers in polar regions learned that the instrument they trusted farther south could become much less reliable when they needed it most. This is a lovely reminder that scientific tools are shaped by assumptions about the environments where they will be used. A compass is not a magical oracle. It is a clever device working within physical limits. Near the poles, Earth reveals those limits very clearly. The same planet-wide force that makes compasses useful can also make them act strangely when its geometry becomes extreme. Some animals carry microscopic crystals that may sense magnetism. One of the most intriguing ideas in animal navigation is that some creatures may carry tiny crystals of magnetite inside their bodies. Magnetite is a naturally magnetic mineral, and at microscopic scales it could, in principle, respond to Earth's field and help living tissue detect direction or position. Researchers have searched for such particles in birds, fish, insects, and other animals, hoping to understand how biology might convert magnetism into sensation. The evidence has been complex and sometimes debated, which only adds to the fascination. If the idea is correct in particular cases, then evolution has done something extraordinary. It has taken a mineral humans use in compasses and woven it into the machinery of life. Imagine that for a moment. An animal might carry tiny bits of magnetic matter as part of its own internal guidance system. That possibility makes the boundary between geology and biology feel unexpectedly thin, as if the planet's deep minerals have found a second life inside living bodies. Sea turtles may memorize magnetic maps of the oceans. A young sea turtle entering the open ocean faces a world that seems impossibly vast. There are no roads, no signposts, and often no obvious landmarks at all. Yet these animals can travel astonishing distances and later return to feeding grounds or nesting regions with impressive accuracy. One idea supported by experiments is that they can detect features of Earth's magnetic field, such as intensity and inclination, and use those cues as part of a kind of map. Different parts of the ocean have different magnetic signatures, and turtles may learn to recognize them. That means the sea itself may be patterned in a way the animals can read, even though humans cannot sense it directly. The image is wonderful. A hatchling vanishes into blue immensity, carrying not a paper chart, but a biological ability tuned to the planet. The ocean looks empty to us, yet to a turtle, it may be full of invisible landmarks waiting to be remembered. Salmon, they use magnetic clues to cross vast seas. Salmon are famous for their return journeys, but one of the most astonishing parts of their story happens long before they reach their home rivers. After heading out into the ocean, they can roam through immense marine spaces and later find their way back with striking precision. Experiments suggest that Earth's magnetic field may help guide parts of this voyage. By detecting patterns in the field, salmon may gain information about latitude or large-scale position while they move through the sea. This does not mean magnetism is their only guide. Smell and other environmental cues matter deeply, especially near rivers. But the magnetic component makes the journey feel even more extraordinary. These fish may carry within them a way of reading the geometry of the planet while swimming through waters that seem featureless to us. A salmon cutting through cold ocean swells may therefore be doing more than enduring a hard migration. It may be navigating with a sense humans never possessed. Honeybees can react to magnetic fields we cannot feel. Honeybees already seem remarkable because they navigate, communicate, and organize their societies with such precision. Magnetism adds another layer to that mystery. Studies have suggested that bees can respond to magnetic fields, which means part of their awareness may include a cue entirely absent from ordinary human experience. Researchers have explored whether magnetic sensitivity helps with orientation, nest behavior, or the interpretation of space during foraging. The details are still being refined, but even the possibility is captivating. A bee moving from flower to flower may be gathering more than scent, color, and sunlight. It may also be registering part of the planet's invisible framework. That idea changes the feel of a garden. What looks peaceful and familiar to us may be filled with signals another creature can detect and use. Magnetism then becomes not just a force of machines and planets, but part of the hidden sensory world of a small insect whose life already seems finely tuned beyond anything its size would suggest. Even bacteria can swim by following Earth's magnetic field. Some of the strangest navigators on Earth are not birds or turtles, but bacteria. Magnetotactic bacteria contain chains of tiny magnetic crystals inside their cells, and those crystals act like microscopic compass needles. The effect helps the bacteria align with Earth's magnetic field as they swim. For such tiny organisms, this guidance can be very useful because it helps them move efficiently toward environments with the right chemical conditions, often where oxygen levels suit their needs. The wonder here comes from scale. We usually think of magnetism in terms of large machines, powerful fields, or dramatic natural events. Yet single cells can also make use of it, turning a planetary force into practical behavior. These organisms are doing something that sounds almost fantastical. They build internal magnetic structures and use them to orient themselves in the world. That means the influence of Earth's field reaches all the way down into microbial life, guiding creatures so small that millions could fit inside a raindrop. Sharks can detect electric signals linked to magnetism in water. Sharks move through the sea with senses that feel almost alien, and one of their most extraordinary abilities involves the detection of faint electric fields. Special organs called ampullae of Lorenzini allow them to pick up tiny electrical signals produced by muscles, nerves, and even the heartbeat of hidden prey. Magnetism enters the story because moving through Earth's magnetic field can induce weak electric effects in seawater and in the shark's own body. That means a magnetic landscape may become partly detectable through an electrical sense. Researchers are still studying how much this helps with navigation, but the possibility is thrilling. A shark may not need to sense magnetism in the same way a compass does. It may instead feel consequences of magnetism through the conductive world around it. The ocean then becomes an active field of subtle information. For an animal already built for precision hunting, that invisible layer could provide orientation in waters that seem blank and endless to human eyes. Pigeons became famous because they can navigate with magnetic help. Pigeons earned their reputation through an ability that once seemed almost miraculous. Released far from home, they could often return with impressive reliability, crossing unfamiliar terrain as if carrying a secret map. For years, people wondered how they managed it. The answer appears to involve a combination of cues, including landmarks, the sun, smell, and magnetic information. That last element is one reason pigeons became so important in studies of animal navigation. They offered a familiar, testable example of a creature that might be using Earth's field as part of its orientation system. What makes them especially fascinating is their ordinariness. They are not exotic deep-sea wanderers or rare Arctic migrants. They are birds many people barely notice in city streets. Yet inside that ordinary creature lies a navigational toolkit sophisticated enough to challenge human intuition. A pigeon lifting into the sky may look commonplace, but it carries with it one of the most quietly astonishing abilities in the animal world. Magnetism and electricity are really two sides of one force. For a long time, electricity and magnetism seemed like separate mysteries. One made sparks leap and charges flow. The other pulled iron and turned compass needles. Then scientists discovered that the two are deeply linked. A moving electric charge creates a magnetic field, and a changing magnetic field can drive electric charge into motion. Together they form electromagnetism, one of the fundamental forces of nature. This is one of the great unifications in science, because two strange phenomena turned out to be parts of the same deeper story. It explains lightning, radio waves, motors, generators, and the light reaching your eyes right now. That last part is especially astonishing. Visible light itself is an electromagnetic wave. So the same grand framework that explains a fridge magnet also explains sunshine and starlight. Few ideas expand so dramatically once you open them up. What begins with a simple magnet on a table quickly grows into one of the most powerful descriptions humans have ever found for the universe. Moving a magnet can create electricity from empty stillness. One of the most magical moments in physics is watching a coil of wire and a magnet bring electricity into being. Nothing seems connected. No battery is attached. No fuel is burning. Yet move the magnet near the coil, and a current appears. The secret is that a changing magnetic field pushes electric charges inside the wire, setting them in motion. This principle is called electromagnetic induction, and it changed the world. It means motion can become electricity through magnetism alone. That idea opened the door to modern power generation and countless devices besides. There is something deeply satisfying about how direct it feels. Motion on one side, current on the other, with invisible field changes serving as the translator. The still coil seems lifeless until the magnet moves. Then suddenly, the system wakes up. It is hard not to feel a little awe at that transformation. A hand motion can become electrical flow, and the bridge between them is an unseen structure in space. Every power station depends on magnets turning motion into current. Whether a power station burns fuel, splits atoms, harnesses falling water, or captures wind, the final act is often astonishingly similar. Something turns a turbine. The turbine spins a generator. And inside that generator, magnets and coils work together to produce electric current. In other words, the lights in a city may begin with steam, water, gas, or wind, but they usually reach the grid through magnetism. This is one of the hidden consistencies of modern life. Many energy sources look different at the surface, yet deep inside the machinery, the same electromagnetic principle is doing the essential work. Rotation becomes current because magnetic fields change across conductors in carefully engineered ways. It is a beautiful conversion, and it happens on an enormous scale every day. Streets glow, trains run, hospitals function, and homes stay lit because generators keep translating motion into electricity. Behind much of civilization stands a spinning machine and the invisible force that makes it useful. Electric motors work because magnetic forces turn energy into motion. A motor is one of the clearest examples of magnetism becoming movement. Feed electrical current into the right arrangement of coils and magnetic fields, and parts of the machine begin to push and pull against each other in a repeating pattern. That interaction creates rotation, and rotation can drive almost anything, from a fan blade to a factory conveyor to the wheels of an electric car. What makes this so captivating is the elegance of the conversion. Electricity arrives unseen through wires, then magnetism takes over and transforms that invisible flow into physical motion you can hear, watch, and feel. Motors are everywhere, which can make them easy to overlook. Yet each one is a small masterpiece of controlled force. Hidden inside a washing machine or power tool is a choreography of changing fields producing useful work with extraordinary reliability. Once you understand that, ordinary machines begin to feel newly alive. They are not merely moving. They are performing magnetism in motion, all around us. Speakers make music by moving magnets back and forth. When music pours from a speaker, magnetism is part of the performance. Inside the speaker, an electrical signal carrying the shape of the sound flows through a coil of wire placed within a magnetic field. As the signal changes, the coil experiences changing forces and moves back and forth. That motion drives a cone, and the cone pushes air into vibrations your ears can hear as voice, melody, rhythm, or thunder. It is a wonderful chain of transformation. A singer's breath becomes an electrical pattern. That pattern enters a speaker. Magnetism turns it into motion again. Motion stirs the air. Then your ear and brain turn those pressure waves back into experience. The speaker itself may look like an ordinary object on a shelf, but it is really a translator between electricity and sound. Every whispered lyric and crashing drumbeat depends on tiny controlled movements powered by magnetic force. In that sense, magnetism is not only moving metal, it is helping carry emotion through the air. Microphones reverse the trick, turning motion into electrical signals. A microphone performs the opposite transformation to a speaker, and that reversal is part of its elegance. Sound waves arrive through the air and make a thin diaphragm vibrate. In many designs, that motion moves a coil within a magnetic field or changes the relationship between magnetic parts, and the result is an electrical signal that mirrors the original sound. A voice becomes current. A guitar string becomes voltage. A laugh, a breath, or a footstep becomes something a recording system can store, send, and amplify. This is one of those technologies that feels ordinary only because it works so well. The moment you speak into a microphone, delicate air ripples are being translated into electrical form with extraordinary sensitivity. That process allows concerts, podcasts, films, and phone calls to exist in the ways we know them. Magnetism helps capture the fleeting texture of sound and turn it into something portable. It takes a passing vibration and gives it a second life inside a machine. Transformers use magnetism to move energy between separate circuits. A transformer is a remarkable device because it can transfer electrical energy from one circuit to another without the two circuits touching directly. It works through a shared magnetic field. Alternating current in one coil creates a changing field in an iron core, and that changing field induces current in a second coil nearby. The result is a controlled handoff of energy across a small gap, guided by magnetism rather than by direct electrical connection. This matters enormously because transformers can raise or lower voltage, making long-distance power transmission practical and efficient. Without them, modern electrical grids would be far more limited and wasteful. What makes the device so satisfying is its quiet cleverness. Nothing dramatic seems to happen from the outside. No sparks leap. No gears turn. Yet inside, energy is being reshaped and relayed by an invisible field. Entire power networks depend on this elegant exchange, where magnetism serves as a mediator between circuits that never actually meet. Induction cookers heat pans using fast-changing magnetic fields. An induction cooker can seem almost uncanny the first time you see one in action. The surface may stay relatively cool, yet a suitable pan placed on top begins heating rapidly. The reason lies in changing magnetic fields produced by coils beneath the cooktop. Those fields induce electric currents inside the metal of the pan, and the resistance of the metal turns that electrical motion into heat. In other words, the cooker does not simply warm the surface and hope the pan follows. It drives energy directly into the cookware itself. That is what makes the method efficient and responsive. It also makes the experience feel strangely futuristic, because the heat appears exactly where it is needed with very little delay. Magnetism is doing culinary work. An invisible field is reaching into a pan and stirring charges until dinner begins to sizzle. Few kitchen technologies reveal physics so beautifully. A meal starts not with flame or blowing coils, but with carefully shaped electromagnetic motion. Wireless chargers use magnetism to send power across small gaps. Wireless charging feels like a small, everyday miracle. You set a phone or earbuds case onto a pad, and energy begins to flow without any exposed metal contacts needing to mate in the usual way. The underlying idea is closely related to induction. A coil in the charger produces a changing magnetic field, and a matching coil in the device receives energy from that field and converts it back into electrical current for the battery. The gap may be tiny, but the principle is profound. Power is crossing space through organized electromagnetic interaction. That makes the technology feel strangely elegant, almost ceremonial. Place the device down, align it well, and it begins to drink energy from an invisible link. Of course, the range is limited, and the system is less dramatic than science fiction beams across a room. Even so, it shows how magnetism can make ordinary life feel a little more advanced. Charging becomes less like plugging in a machine and more like setting up a controlled field relationship. Maglev trains float because magnets can lift enormous weight. A maglev train turns one of magnetism's most surprising abilities into transportation. By using powerful magnetic forces, the train is lifted above its track so that there is little or no direct contact between moving parts. That removes much of the friction that slows ordinary rail systems, allowing for very high speeds and a smooth, gliding ride. Different systems achieve this in different ways, but the central wonder remains the same. Weight that seems overwhelming can be countered by invisible force. A vehicle carrying many passengers can hover just above a guideway and surge forward with astonishing efficiency. It feels like a technology borrowed from the future, yet it rests on physical principles discovered long ago. What makes it so compelling is the combination of scale and grace. We are used to the idea that heavy machines grind, rumble, and wear against rails. A maglev challenges that expectation. It shows that magnetism can lift, guide, and propel immense mass with startling elegance. MRI scanners use magnets to look inside living bodies. An MRI scanner reveals the interior of the body by taking advantage of one of the smallest magnetic features in ordinary matter. Much of you is made of water, and the hydrogen atoms in that water behave a little like tiny spinning magnets. Inside the machine, an intense magnetic field encourages vast numbers of those atoms to line up in a particular way. Then, pulses of radio energy disturb that alignment. As the atoms relax, they release signals that can be measured and turned into detailed images. Different tissues respond in different ways, which allows doctors to distinguish structures that would otherwise remain hidden. What makes this so astonishing is the scale of the translation. A force rooted in atomic behavior becomes a picture of the knee, the spine, the liver, or the brain. Hidden anatomy is not pried open. It is coaxed into revealing itself. The body becomes readable because magnetism can organize matter and listen to the answer. Hospitals rely on superconducting magnets colder than outer space. Many of the most powerful medical magnets are made from superconducting materials, and those materials only work properly when cooled to extraordinary temperatures. In practice, that often means being chilled with liquid helium, until they are only a few degrees above absolute zero. That is colder than the natural temperature of much of outer space, which is a startling fact to carry into a hospital corridor. At those extremes, electrical resistance drops away, allowing powerful currents to flow in coils without the usual energy loss. That makes it possible to generate magnetic fields strong enough for demanding medical imaging. There is something almost poetic about this. To see living tissue in fine detail, hospitals depend on machinery operating in a state of cold, more severe than the dark between stars. A patient lies in a bright clinical room, yet nearby a magnet is being maintained in conditions that sound cosmic and unreal. Modern medicine often looks calm on the surface, while extraordinary physics hums underneath. Particle accelerators steer shattered atoms with giant magnetic fields. Inside particle accelerators, magnetism becomes a tool for guiding matter at tremendous speed. Charged particles, such as protons or electrons, race through long tubes or giant circular tunnels, and magnetic fields bend and focus those beams with exquisite precision. Without that control, the particles would simply fly off course. With it, scientists can guide them into collisions or send them cleanly into detectors designed to catch the aftermath. This is how researchers study some of the smallest ingredients of nature. By smashing particles together at enormous energies, they can reveal short-lived fragments, new interactions, and hidden patterns in matter itself. The magnets involved are not decorative supports to the real experiment. They are essential actors in it, shaping the paths of particles that no human eye could ever see. It is a thrilling thought that colossal machines use invisible force to choreograph subatomic impacts. Magnetism helps turn abstract physics into events that can actually be measured and understood. Fusion reactors try to cage star-hot plasma with magnets. Fusion aims to copy the power source of stars here on Earth. The fuel must be heated until it becomes plasma, a state in which electrons are stripped from atoms and the whole substance becomes electrically charged. At that temperature, no ordinary container can hold it. Any solid wall would be overwhelmed. Magnetism offers another approach. Because plasma contains charged particles, strong magnetic fields can guide and confine it, keeping the blazing material suspended away from the reactor walls. Devices such as tokamaks and stellarators are built around this idea. They try to hold a miniature starfire in place long enough for fusion reactions to release useful energy. The challenge is immense, because the plasma writhes, shifts, and resists control. Yet the ambition is breathtaking. Humans are attempting to bottle one of the universe's great energy sources using invisible force alone. Magnetism becomes not just a scientific tool, but a possible bridge to an entirely new energy future. Magnets help sort scrap metal from mountains of waste. In recycling yards, magnetism performs a kind of industrial triage. Vast heaps of discarded objects arrive mixed together, from twisted car parts to broken appliances and shredded construction debris. Pulling out the useful ferrous metal by hand would be slow, dangerous, and wildly inefficient. Instead, powerful magnets sweep across conveyor belts or hang from cranes, lifting iron and steel away from plastic, wood, glass, and non-magnetic metals. This helps turn chaos into separated streams of material that can be reused. The process may look rough and dirty, but the underlying principle is elegant. An invisible field becomes a sorting language. One class of material answers, while another stays behind. That simple difference has enormous consequences for industry and the environment. Recycling becomes faster, safer, and more economical because magnetism can make decisions at scale. A scrapyard may seem like the end of an object's story, yet magnets help turn it into the beginning of another, drawing tomorrow's raw material out of yesterday's waste. Credit cards once stored data in tiny magnetic patterns. For decades, one of the most familiar uses of magnetism lived in wallets and purses. The dark stripe on the back of a credit card was not merely a design feature. It was a band of magnetic material encoded with tiny patterns that represented information the reader could interpret. When the card was swiped, the machine sensed changes in magnetization along the stripe and translated them into usable data. It was a wonderfully physical form of information storage. Your account details were not floating in some distant cloud alone. They were inscribed as magnetic arrangement on a strip you could hold between two fingers. That made everyday payment depend on the same broad principles that govern far grander technologies. There is something charming about that older system. A simple swipe across a reader became a moment where magnetism and commerce met. Though many newer methods have taken over, the magnetic stripe remains a reminder that invisible force once traveled quietly through ordinary transactions. Hard drives remember your files with magnetic domains. Inside a traditional hard drive, data lives as patterns of magnetized regions written onto spinning disks. Those regions are called magnetic domains, and each one can be oriented in a way that represents part of digital information. A write head changes the orientation in selected spots. Later, a read head detects those differences as the disk spins beneath it. That is how documents, photographs, songs, and software can persist inside a machine long after the screen goes dark. The marvel lies in the contrast between the ordinary and the microscopic. A family photo may look warm and personal on a monitor, yet inside the drive it exists as a precise magnetic arrangement on a thin surface moving at high speed. Entire libraries can be held this way. Years of work, memory, and art can rest in magnetic order smaller than the eye can resolve. Storage feels abstract when we speak about files, but in a hard drive, memory is literally written into matter by magnetism. The tiny stripes on tickets once held magnetic information. For many years, transport systems, hotel systems, and access systems relied on small magnetic stripes embedded in tickets and passes. A train ticket, a subway card, or a room key could carry information in a narrow band of magnetized material. When fed through a reader, that stripe delivered instructions about access, identity, or fare status. The object itself might feel flimsy and forgettable, yet it contained machine-readable information encoded by magnetic pattern. That is part of what makes the old technology so delightful to remember. Everyday travel was full of invisible interactions. A barrier opened. A gate clicked. A door unlocked. Behind the convenience was a tiny magnetic memory traveling in your pocket. These systems also gave physical movement a satisfying ritual. You inserted, swiped, or tapped a ticket into place, and the hidden code did its work. Long before many people thought about digital systems as something abstract and wireless, magnetism was already managing ordinary journeys in plain sight. Magnetic sensors quietly sit inside phones, cars, and satellites. Magnetic sensors are among the most easily overlooked pieces of modern technology because they do their work silently and invisibly. In a phone, they can help determine orientation and direction by detecting Earth's field. In a car, they may monitor wheel speed, motor position, or the movement of mechanical parts. In satellites, they can help with attitude control and navigation by sensing the magnetic environment around the spacecraft. The beauty of these devices is that they turn magnetic changes into information. A field shifts, a component moves, a wheel rotates, and the sensor reports it. That makes them less like magnets in the familiar household sense and more like interpreters of hidden conditions. The world is full of signals humans cannot directly perceive, and these sensors translate some of them into useful data. They are small, often invisible to the user, yet they help machines know where they are, how fast they are moving, and how they are positioned in space. Some door locks open with magnetism instead of keys. Not every lock depends on a shaped metal key turning inside a cylinder. Some rely on magnetic principles to grant entry. In certain designs, a magnetic card or coded magnetic element triggers the internal mechanism. In others, an electromagnet holds a door secure until power is cut or a control signal releases it. This gives builders and engineers options that suit hotels, offices, secure facilities, and systems requiring remote control. What makes these locks interesting is not only convenience, but the shift in how we imagine access itself. Entry no longer depends entirely on teeth-fitting grooves. It can depend on invisible fields, encoded patterns, and controlled electrical states. A door that opens may be responding not to forceful turning, but to a magnetic conversation inside the hardware. That gives a familiar object an unexpectedly modern character. Even something as ancient as locking and unlocking has been transformed by magnetism, which now stands quietly behind many moments when a barrier decides to yield. Fridge magnets are weak, but industrial magnets can be terrifyingly strong. A fridge magnet belongs to the friendly end of the magnetic world. It can hold a postcard, a shopping list, or a child's drawing, and that seems to define the force as harmless and domestic. Then you step into an industrial setting, and the scale changes completely. There, magnets can drag steel plates, lift wreckage, or seize tools from a distance with alarming speed. The difference is not just a matter of size, but of design, material, and purpose. Industrial systems are built to exert force on heavy ferrous objects in demanding environments, and they do it with a confidence that can feel almost predatory. A misplaced wrench can become a projectile. A steel beam can answer invisible force before a person has time to react. That contrast is part of what makes magnetism so gripping. The same basic phenomenon that decorates a kitchen can, in another context, become powerful enough to rearrange machinery and demand real respect. Neodymium magnets are among the strongest permanent magnets ever made. Neodymium magnets changed what people expect from a magnet that needs no power supply. Made from alloys that include rare earth elements, they pack extraordinary magnetic strength into surprisingly small pieces. A disc that fits in your palm can feel almost absurdly powerful, snapping towards steel with a speed that catches people off guard. This matters because it allows engineers to build smaller, lighter, and more efficient devices. Strong, permanent magnets make better headphones, compact motors, precise tools, and countless other technologies possible. There is something almost shocking about how much force can be hidden inside such a modest object. You hold a small grey piece of material, and it behaves with the authority of something far larger. That mismatch between appearance and ability is part of the fascination. Neodymium magnets remind us that magnetism is not always about huge machinery. Sometimes the most impressive examples are the ones that fit between your fingertips and still feel astonishingly strong. A small, rare earth magnet can pinch skin painfully hard. The danger of a strong, small magnet often comes from how innocent it looks. A rare earth magnet may be no bigger than a coin or a bead, yet when two of them rush together, they can trap skin with startling force. Fingers caught between them can be bruised in an instant. The pain surprises people because the object seems too small to do real harm. That is what makes these magnets such effective teachers of scale and hidden strength. Force does not always advertise itself with bulk. In some cases, it hides inside compact materials and appears only when motion begins. Anyone who has handled powerful little magnets knows the moment of regret. One slips, another answers, and the gap vanishes before you can react. The lesson is memorable because it is physical and immediate. Magnetism stops being an abstract property and becomes something you feel sharply. A tiny object suddenly reveals itself as far more serious than it first appeared. Strong magnets can shatter if they slam together unexpectedly. People often imagine magnets as sturdy objects because they feel so forceful in the hand. Yet some of the strongest permanent magnets are also surprisingly brittle. When two snap together from even a short distance, the collision can be violent enough to chip, crack, or shatter them. Tiny, sharp fragments may fly off, which is why eye protection is recommended in some settings. This is such an interesting contradiction. The magnets act powerful, even aggressive, but the material itself can behave more like hard ceramic than resilient metal. Great strength in magnetic performance does not always mean toughness in impact. That contrast gives the subject a strange elegance. A magnet can pull with impressive authority and still be vulnerable to its own sudden success. It is another reminder that properties in physics rarely travel alone. Power is often paired with a weakness somewhere else. In this case, invisible attraction can create an impact harsh enough to destroy the very objects producing it. Magnets can erase data if they overwhelm magnetic storage. For years, one of the quiet risks around magnetic technology was that a strong external field could disturb stored information. If data is encoded as magnetic orientation on a strip or disk, then a sufficiently intense field can scramble that arrangement and make the original information unreadable. This gave magnets a slightly mischievous reputation in the age of floppy disks, cassette tapes, and magnetic cards. A handbag clasp, a speaker, or an ill-placed magnet near storage media could become a small disaster. What makes this so fascinating is the fragility of information in physical form. A file or recording can seem intangible when you think about it, yet on magnetic media, it depends on orderly microscopic patterns that must remain undisturbed. Break that order, and memory dissolves. A song, a document, or an account record may suddenly vanish into noise. Magnetism, which so often helps store and move information, can also be the force that quietly wipes it away when the balance is upset. MRI rooms ban loose metal because magnets can turn it dangerous. The magnetic field around an MRI scanner is so strong that ordinary objects can become hazards in a moment. A pair of scissors, a tool, or even an oxygen cylinder can be pulled toward the machine with frightening speed if brought too close. This is known as the projectile effect, and it is one reason MRI safety is taken with such seriousness. The scanner does not need to be making noise or taking pictures for the risk to exist. The field is often present continuously, waiting silently in the room. That creates a strange atmosphere around the machine. It looks still and controlled, yet it imposes rules on everything nearby. Staff must screen patients for implants, remove metal items, and protect the space with strict procedures. What fascinates people is how quickly the familiar can become dangerous. An everyday object that feels harmless in one room can become a missile in another, simply because magnetism there is operating on an entirely different level. A superconducting magnet can keep working with almost no resistance. In ordinary wires, moving electric current meets resistance and loses energy as heat. Superconductors break that expectation. When cooled enough, certain materials allow current to flow with essentially no electrical resistance, which means powerful currents can circulate for extremely long periods without the usual loss. Build coils from such material, and you can create magnets of extraordinary strength and efficiency. This feels almost like a loophole in the normal rules of engineering. Energy is not being fought away as waste heat in the usual manner. Instead, the current can persist with astonishing stability, making superconducting magnets invaluable in research, medicine, and advanced technology. There is a quiet grandeur to that idea. A loop of current can keep circling through an icy material, maintaining an intense magnetic field, as though friction had been almost erased from the electrical world. Magnetism here becomes a showcase for one of physics' most beautiful states, where cold unlocks behavior that seems nearly impossible. Some materials become perfect diamagnets when they turn superconducting. When a material enters the superconducting state, something extraordinary can happen beyond the loss of resistance. It can expel magnetic fields from its interior, a phenomenon known as the Meissner effect. In practical terms, the superconductor behaves like a perfect diamagnet, pushing magnetic field lines away rather than letting them pass through as they normally would. This is one of the reasons superconductors can levitate above magnets or lock into stable positions in striking demonstrations. The sight feels unreal because it seems to show matter rejecting magnetism so completely that gravity loses its usual authority. Yet the deeper wonder is conceptual. A material changes state, and with that change comes a new relationship to magnetic fields altogether. The field is not merely weakened or redirected a little, it is actively excluded. Few transitions in physics feel so dramatic. A cold enough material stops behaving like its ordinary self and begins acting as though magnetism itself must keep its distance. A frog has been levitated using a powerful magnetic field. One of the most unforgettable demonstrations in modern physics involved a living frog floating in mid-air inside a strong magnetic field. The effect was not magic, and it was not trick photography. It happened because the water inside the frog, like water generally, is weakly diamagnetic. In an intense field with the right gradient, that subtle repulsion can balance the pull of gravity. The result is levitation of something far larger and stranger than the bits of graphite or metal people expect in a lab demonstration. The frog matters because it transforms an abstract principle into a scene nobody forgets. Suddenly, magnetism is not merely about compasses, motors, or industrial machinery. It is strong enough, under special conditions, to lift a small animal bodily into the air. That image stretches the imagination. It shows how effects that seem tiny in daily life can become spectacular when the field grows powerful enough. Physics moves from textbook concept to unforgettable spectacle in one leap. Water is weakly repelled by magnets, including the water in you. Most people do not think of water as magnetic in any meaningful sense, yet it does respond, just very faintly. Water is diamagnetic, which means it is weakly repelled by magnetic fields. The effect is tiny under ordinary conditions, so you would never notice it around common household magnets. But in very strong fields, the response becomes real enough to measure and sometimes dramatic enough to demonstrate. That matters because your body is made largely of water. In a subtle sense, part of you is always participating in this magnetic behavior too. This does not mean a normal magnet can push you around, of course. The effect is far too weak for that in everyday life. What makes the fact so wonderful is the shift in perspective it creates. Magnetism is not only about iron and steel after all. Even a glass of water, a raindrop, or the water within living tissue has a place in the story, quietly answering powerful fields in its own delicate way. Graphite can float above magnets because of diamagnetism. A thin piece of graphite can do something that looks like a conjuring trick. Place it above a carefully arranged set of strong magnets, and it can hover in stable balance instead of falling straight down. The reason is that graphite is diamagnetic, which means it develops a very slight opposition to an applied magnetic field. Usually that effect is so weak you would never notice it. But graphite shows the response more strongly than many familiar materials, and with the right setup, the tiny push becomes enough to support its weight. What makes the demonstration so memorable is its elegance. There are no hidden threads, no moving parts, and no humming machinery. A dark little fragment simply hangs above the magnets as if gravity has been persuaded to loosen its grip. It is one of the best reminders that magnetism is not only about attraction. Sometimes the most astonishing behavior begins when a material chooses, ever so slightly, to push away. Not all metals are magnetic, and that surprises many people. Many people grow up with the simple idea that metal and magnets belong together. Then reality interrupts. A magnet clings firmly to one object and ignores another made of metal entirely. That surprise is useful because it reveals that magnetism depends on internal structure rather than on the broad label of metal alone. Some metals have atoms whose magnetic behavior can align in a cooperative way. Others do not. That is why a steel nail may leap toward a magnet while a coin, a copper wire, or a sheet of aluminum barely responds in the same familiar fashion. The difference feels almost unfair until you realize nature is being specific. Chemistry, crystal structure, and electron behavior all matter. This makes the metal world much more interesting than the old simplification suggests. A shiny surface tells you almost nothing about magnetic character. Two objects can look equally metallic to the eye, yet inside they belong to very different magnetic stories. Iron, cobalt, and nickel are the classic magnetic elements. When people think of strongly magnetic materials, three elements sit at the center of the conversation. Iron, cobalt, and nickel are the classic examples because they can become ferromagnetic, meaning large numbers of atomic magnetic moments can line up together and create a strong overall effect. That shared tendency gives them a special place in science, industry, and ordinary experience. Iron has shaped the story most deeply because it is abundant and practical, showing up in tools, machinery, buildings, and the very core of the planet. Cobalt and nickel are less familiar to many people, yet they are equally important in understanding how strong magnetic behavior arises. What makes these elements so captivating is that they reveal a rare kind of teamwork at the atomic level. Countless tiny contributors begin acting in concert, and the result is a material that can grip, guide, store information, or drive machines. Strong magnetism is not just about force. It is about remarkable internal agreement. Copper is famous in electricity, but it is not ferromagnetic. Copper has earned its place in human technology through electrical talent rather than strong everyday magnetism. It carries current beautifully, which is why it fills wires, motors, circuits, and power systems across the modern world. Yet place a typical magnet beside a copper pipe or copper coin, and you will not get the dramatic attraction many people expect. This contrast is fascinating because it separates two ideas that are often blurred together in the public imagination. Electricity and magnetism are deeply linked, but a material can excel in one part of that partnership without behaving like a classic permanent magnet. Copper is a perfect example. It is indispensable to electromagnetic technology while remaining outside the familiar ferromagnetic club. That gives the metal a subtle elegance. It works behind the scenes, carrying charge, shaping fields, and enabling devices, while refusing the theatrical leap toward a fridge magnet. Sometimes the most important materials are the ones whose gifts are powerful but less obvious. Aluminum is not strongly magnetic, though fields still affect it. Aluminum often surprises people because it looks metallic, feels industrial, and appears in everything from kitchen foil to aircraft parts, yet it does not cling to a household magnet in the usual way. That can make it seem magnetically irrelevant, but the truth is far more interesting. Aluminum does respond to magnetic fields, just not with the strong ferromagnetic attraction people expect. It is weakly paramagnetic, and moving magnetic fields can also induce currents within it. Those induced currents can create forces that matter a great deal in practice. Drop a strong magnet through an aluminum tube, for example, and it falls strangely slowly because the changing field generates currents that resist the motion. Suddenly, a metal that seemed indifferent begins to reveal hidden complexity. That is what makes aluminum so satisfying in this story. It teaches that magnetic effects are not always obvious at first touch. Sometimes the drama appears only when motion, timing, and field changes enter the scene. Stainless steel can be magnetic, or not, depending on structure. Stainless steel sounds like it should be one thing, but in reality, it is a family of materials with different internal arrangements and different magnetic behavior. Some kinds are strongly attracted to magnets. Others are barely affected at all. The difference comes from crystal structure and composition, which determine how the electrons and atoms organize inside the alloy. This is a wonderful example of how names can mislead us. Two objects can both be called stainless steel and look nearly identical, yet one answers a magnet and the other stays almost unmoved. That small household test hints at a deeper truth in materials science. What matters is not only what elements are present, but how they are arranged. Engineers take advantage of this by choosing specific grades for specific jobs, whether they need corrosion resistance, strength, or magnetic response. So a simple kitchen sink, surgical instrument, or machine part may be hiding a surprisingly rich story about structure and behavior. Temperature can weaken magnetism until it suddenly vanishes. Heat is the great disturber of order, and magnetism is one of the places where that becomes beautifully clear. In a strongly magnetic material, many atomic moments are aligned in a shared direction, producing the large-scale behavior we notice. As temperature rises, thermal motion becomes more violent. The atoms and electrons do not literally fly apart, but their restless jostling makes orderly alignment harder to maintain. For a while, the magnet weakens. Then, at a critical point, the cooperative order collapses, and the familiar, strong magnetism disappears. This feels dramatic because the change is not merely gradual forever. There is a threshold where a material crosses into a different regime of behavior. The magnet that once acted decisive and strong becomes something else under sufficient heat. It is a striking reminder that magnetism is not fixed once and for all. It depends on the balance between order and agitation, and temperature can tip that balance until the old behavior simply can no longer survive. Every magnet has a limit called the Curie temperature. There is a point beyond which a magnet cannot remain what it was, no matter how well made or how strongly magnetized. That threshold is called the Curie temperature. Below it, the material can sustain the internal alignment needed for ferromagnetism. Above it, thermal agitation overwhelms that order, and the strong magnetic character disappears. The idea is powerful because it gives every magnet a kind of hidden ceiling written into its nature. A magnet may seem solid and dependable in your hand, yet its behavior is only guaranteed within a certain thermal world. Cross that boundary and the old rules fail. Engineers care deeply about this when choosing materials for motors, electronics, and demanding environments, because a device that overheats may also lose crucial magnetic performance. There is something almost philosophical about it. Even a magnet has a breaking point, not through shattering or collision, but through disorder winning from within. Heat does not need to destroy the object to change what it is. Heat can scramble magnetic order inside a once strong magnet. Inside a strong magnet, the microscopic contributors are not acting at random. They are arranged in a pattern that produces a clear, large-scale effect. Add enough heat, and that pattern begins to unravel. The energy of thermal motion shakes the orderly alignment until the internal arrangement becomes confused and fragmented. What used to act like a coordinated crowd starts behaving more like a noisy gathering with no common direction. This is a useful way to picture why heating a magnet can weaken it or even ruin it. The outer shape may look unchanged, but the hidden order that gave the object its power has been disturbed. That makes magnetism feel surprisingly alive, almost social in character. Its strength comes from cooperation, and heat interrupts that cooperation. The result is not always visible at a glance, yet the loss is real. A once reliable magnet may emerge from excessive heat looking the same, while carrying a very different internal story. Cold can help magnets perform more powerfully and efficiently. Lower temperatures often make magnetic systems happier places for order to persist. When thermal agitation is reduced, aligned states can remain steadier, and certain magnetic materials perform more strongly or predictably than they do at warmer temperatures. This can improve efficiency in devices that rely on precise magnetic behavior, especially in advanced engineering and research settings. Cold also matters because it opens the door to materials and regimes that would be impossible at ordinary temperatures, allowing far stronger and more controlled magnetic performance than warmth would permit. What is so fascinating here is the reversal of everyday intuition. We often think of cold as slowing things down and making systems less active. In magnetism, cold can instead reveal hidden excellence. By calming the microscopic disorder that heat encourages, it allows magnetic order to show its full strength more clearly. The invisible force becomes sharper, steadier, and more useful. Sometimes the path to stronger magnetism is not more power, but simply less thermal chaos. Inside a magnet, countless tiny regions line up together. A magnet looks simple from the outside, but inside it there is a remarkable kind of collective order. Rather than every atom acting alone, many neighboring atoms group into regions where their magnetic tendencies point in the same direction. When enough of those regions point compatibly across the material, the whole object develops the large-scale magnetic behavior we can feel. That is what makes a magnet so fascinating. Its strength is not coming from one privileged spot hidden in the center. It emerges from enormous numbers of tiny contributors cooperating across the solid. This turns a chunk of metal into something more like a chorus than a solo performance. Each part matters because it joins a larger pattern. Once you picture that, magnetism feels less like a mysterious property stamped onto matter and more like an organized state the material has achieved. A magnet is powerful not because of one secret ingredient, but because multitudes inside it have settled into agreement. Those tiny regions are called magnetic domains by physicists. Physicists gave a name to those coordinated little patches inside magnetic materials. They call them domains. The word is useful because it suggests territory, and that is very close to the truth. Each domain is a small region where many atomic magnetic moments point in the same general direction. A solid piece of iron can contain huge numbers of these domains, each one like a district with its own preferred orientation. In an unmagnetized object, different domains may point different ways, so the overall effect largely cancels out. In a magnetized object, the balance shifts and some orientations win out over others. What makes domains so captivating is that they turn magnetism into a story of internal landscape. Matter is not simply magnetic or non-magnetic in a bland binary sense. It can contain competing regions, shifting borders, and changing patterns of order. The invisible force we feel outside the material begins as a geography of tiny aligned territories within it. Unmagnetized iron becomes magnetic when domains swing into alignment. A plain piece of iron may seem ordinary and magnetically quiet, yet much of the potential for strong magnetism is already waiting inside it. The domains are there, but they point in many directions, so their effects mostly cancel. Bring that iron into a strong magnetic field, and the balance begins to change. Some domains grow, others shrink. Many swing into more favorable orientations until the material develops a clear overall magnetic character. This is such a beautiful idea because it means magnetization is often less about creating something from nothing and more about persuading existing order to organize itself. The iron was not empty of magnetic possibility. It was internally undecided. A strong field acts like a leader entering a noisy room and gradually bringing the voices into one song. That transformation can happen quickly, yet behind it lies a subtle rearrangement of countless tiny regions. A dull nail or bar can become strikingly different once enough of its inner territories turn the same way. Hitting or heating a magnet can knock its order apart. A magnet keeps its strength only as long as its internal order holds together. Disturb that order hard enough, and the magnet begins to lose what made it special. Heat does this by increasing microscopic agitation, which makes aligned regions harder to maintain. Mechanical shock can also matter. A sharp blow can jostle the internal structure enough to let some regions shift into less orderly arrangements. That is why a magnet can weaken after being struck or badly treated, even if it does not look damaged from the outside. The object may appear unchanged, but the hidden pattern inside has been scrambled. There is something wonderfully revealing in that. Magnetism is not just a hard property glued onto matter forever. It is an organized state that can be preserved, strengthened, or disrupted. A magnet must keep its invisible agreement intact. Shake that agreement loose with heat or impact, and the force you once relied on may fade away. A nail can become a temporary magnet near a stronger one. Place an iron nail near a strong magnet and something subtle begins to happen inside the nail. The external field encourages some of its internal regions to orient in a more ordered way, giving the nail a magnetic character of its own. For a short time, it may even ick up small iron objects such as pins or paper clips. Remove the strong magnet, and much of that borrowed order can fade again, especially if the nail is made of a material that does not hold alignment very stubbornly. This is one of the most charming demonstrations in magnetism because it feels like influence made visible. The stronger object does not merely pull on the nail from outside. It changes the nail's internal state enough that the nail begins acting differently toward the world. In that moment, magnetism looks almost contagious. A simple piece of iron takes on a temporary role it did not seem to possess moments earlier, all because a nearby field persuaded it into cooperation. Electromagnets exist only while electricity keeps their fields alive. An electromagnet is a magnet with a heartbeat of current. Wind wire into a coil, send electricity through it, and a magnetic field appears. Turn the current off, and the field largely disappears. That on-demand quality is what makes electromagnets so useful. Their strength can often be adjusted. Their action can be timed. Their pull can be released instantly when a switch changes state. This gives them a flexibility permanent magnets cannot match. Cranes can lift scrap and then let it go at once. Relays can click on and off in circuits. Machines can use controlled magnetic force only when needed. What makes electromagnets so satisfying is the sense of animation they carry. They are not always magnetic in the same quiet way. They come alive when current flows. The invisible field feels less like a fixed trait and more like an event. Electricity passes through a coil, and suddenly ordinary wire becomes a source of powerful, directed force. Permanent magnets keep their order long after the factory. A permanent magnet earns its name because it can retain magnetic order long after the field used to make it has been removed. During manufacture, the material is exposed to strong magnetizing conditions that push many of its internal regions into alignment. In the right kind of material, that arrangement does not relax easily. the internal structure resists change, so the magnet continues carrying its field through ordinary use. This persistence is what makes a permanent magnet feel so dependable. You can place it in a motor, a latch, a sensor, or a tool and expect it to keep doing its work without a continuing supply of electricity. There is something satisfying about that stability. The object has been trained, in a sense, and it remembers. Long after the machinery of the factory is gone, the order remains stored in the material itself. Magnetism becomes a durable memory inside matter, held there not by constant effort, but by the stubbornness of the internal arrangement. Soft magnetic materials switch easily and are useful in machines. Some magnetic materials are valued not because they cling stubbornly to one state, but because they change their minds quickly and efficiently. These are called soft magnetic materials. They magnetize readily when a field is applied, and they give up that magnetization easily when the field is removed. That makes them ideal for devices where magnetic states must change again and again, such as transformer cores, inductors, and many kinds of electrical machinery. The beauty of these materials lies in their responsiveness. They do not hold on for pride. They cooperate with the demands of the machine. A changing current produces a changing field, and the material follows along without wasting much energy fighting the transition. That makes it a superb partner in systems built around repeated cycles. In a way, soft magnetic materials show a gentler kind of strength. Their value comes not from stubborn persistence, but from adaptability, speed, and a willingness to respond gracefully each time the field shifts. Hard magnetic materials resist change and hold magnetism longer. Where soft magnetic materials are flexible, hard magnetic materials are stubborn. Once magnetized, they resist being demagnetized, which makes them excellent for permanent magnets and applications that need lasting magnetic strength. Their internal structure makes it harder for magnetic regions to shift around, so outside influences have a tougher time undoing the established order. This resistance is deeply useful. A magnet in a motor, speaker, or holding mechanism must keep doing its job over time, often in the face of vibration, stray fields, and ordinary wear. Hard magnetic materials provide that durability by refusing to surrender alignment easily. There is something almost personality-like about them. They are the resolute members of the magnetic family, less eager to change and more determined to preserve what has already been established. That does not make them better in every situation, but it makes them invaluable where persistence matters most. Some machines need materials that hold the line long after the initial push is gone. Engineers shape magnets carefully because geometry changes field strength. A magnet's power is not determined only by what it is made from. Shape matters too. Stretch a magnet into one form and the field may spread broadly. Concentrate it into another and the force may become much stronger in a chosen region. Engineers use this constantly. They adjust length, thickness, curvature, and pole arrangement to control how the field behaves in real devices. That is why magnets appear in bars, rings, discs, arcs, cylinders, and more specialized designs. The goal is rarely just to have a magnet. The goal is to have the right field in the right place with the right intensity and direction. This makes magnet design feel more like architecture than mere manufacturing. Space itself is being organized. A different geometry can change how a motor turns, how a sensor responds, or how securely an object is held. Magnetism is invisible, but shape lets engineers sculpt its behavior. Matter becomes a way of drawing force patterns into the world. Ring magnets create useful fields for motors and sensors. A ring magnet may look simple, almost decorative, yet it is one of the most useful shapes in practical design. Because of its circular form and central hole, it can create magnetic fields that work beautifully in rotating systems, position detectors, and compact mechanisms. A shaft can pass through the middle. A sensor can read changes as the ring turns. A motor can use the symmetry to produce steady, controlled action. This is one reason ring magnets appear in so many devices without drawing attention to themselves. Their geometry fits motion naturally. What makes them so satisfying is the elegance of the arrangement. The field is not merely present. It is organized around a form that invites spinning, alignment, and measurement. That gives the ring magnet a very different character from the classic bar or horseshoe. It feels less like a classroom object and more like a hidden specialist, quietly shaping how machines move, sense, and respond in the modern world. Some toys reveal field lines with dancing iron filings. Few demonstrations capture the imagination faster than scattering iron filings around a magnet and watching them spring into pattern. At first, the filings lie in a messy dust. Then the magnetic field takes command. Each tiny fragment becomes magnetized and rotates into place, forming graceful arcs and dense clusters that trace the shape of the invisible force. In toys and classroom displays, this effect can feel almost alive. Tap the surface, and the filings dance, rearranging themselves as though answering a hidden conductor. What makes the experience so powerful is that it turns abstraction into sight. Magnetism stops being a word and becomes a visible pattern spread across the page. Children and adults both feel the same spark of surprise. Empty space was not empty after all. It had structure waiting to be revealed. The iron filings do not create that structure. They simply expose it, showing that the world around a magnet is organized by lines of influence our eyes normally miss. Ferrofluid turns magnetic fields into spiky black sculptures. Ferrofluid looks like something borrowed from science fiction. It is a liquid filled with tiny magnetic particles, and when a magnetic field is brought near, the surface rises into dark, glossy spikes that shift and cluster in mesmerizing patterns. The effect is so dramatic because it makes magnetism look almost touchable. Instead of an invisible field acting in silence, you see a liquid landscape suddenly growing peaks and ridges, as though the force itself has become visible sculpture. Yet the beauty is not just visual. Ferrofluid shows how matter can reorganize in response to magnetic influence, balancing attraction, repulsion, gravity, and surface tension all at once. That is why the patterns feel both artistic and deeply physical. A simple magnet placed beneath a container can turn still fluid into a moving performance. Few materials reveal the personality of magnetic force so vividly. The field does not merely pull. It shapes, organizes, and transforms a liquid into a living geometry. Magnetic field lines are visual guides, not physical threads. When people first see drawings of magnetic field lines, it is easy to imagine them as real threads stretched through space like invisible wires. They are not. Field lines are a human way of mapping direction and strength, a visual language that helps us picture how the field behaves at different points. The lines show where a small test magnet would tend to align, and how concentrated the influence is in one region compared with another. This matters because the drawings are so persuasive. They look tangible. They curve, loop, and crowd together in ways that feel almost architectural. Yet the lines are a guide, not a hidden material woven through the air. That distinction is part of the beauty of physics. Sometimes the best way to understand a force is to invent a picture that captures its behavior without pretending the picture is literally the thing itself. Field lines are one of science's most elegant sketches of an unseen reality. A magnet's pull weakens quickly as distance increases. Magnetism can feel dramatic at close range. A paperclip snaps across a gap. A tool jumps toward a surface. Two strong magnets rush together with alarming speed. Yet that force fades surprisingly fast as distance grows. Move an object a little farther away, and the effect can drop from impressive to barely noticeable. This is one reason magnets sometimes seem temperamental to people first experimenting with them. They are not weak, in general. They are intensely local. Their influence is strongest when the geometry is favorable and the gap is small. That has huge practical consequences. Engineers must place magnets carefully in motors, sensors, locks, and medical devices because a modest change in spacing can change performance dramatically. What makes this so interesting is the contrast between invisibility and precision. A magnetic field spreads through space, but not with equal usefulness everywhere. Distance shapes the drama. Near the magnet, the force feels immediate. Step back, and the invisible grip loosens with surprising speed. Opposite poles attract, but like poles, stubbornly resist. This is one of the first lessons people learn about magnetism, yet it never loses its charm. Bring opposite poles together, and they rush toward each other with a certainty that feels almost eager. Turn one magnet around so that like poles face, and the mood changes completely. Instead of joining, the magnets push apart. Hold them in your fingers, and you can feel that invisible refusal. It is a wonderfully direct encounter with a force field. Nothing visible stands between the objects, yet the resistance is real and unmistakable. What makes this so fascinating is the clarity of the rule. Magnetism offers both welcome and rejection, depending entirely on orientation. A small rotation can transform attraction into resistance. That gives the force an almost conversational quality. The magnets are not merely moving. They are responding to how they are introduced. Even a child playing with bar magnets gets to feel one of the cleanest and most memorable patterns in all of physics. No one has ever found a lone magnetic pole. Magnets always seem to arrive as complete pairs. Every ordinary example has both a north-seeking side and a south-seeking side. And even when a magnet is cut apart, each new piece forms the same pair again. That is one of the strangest features of magnetism. We are used to the idea that opposites can sometimes be separated, yet magnetic poles remain stubbornly linked in every everyday material anyone has tested. This gives magnetism a different flavor from electric charge, where positive and negative can exist independently. With magnets, isolation refuses to show itself. The phenomenon is so consistent that it shapes the entire way magnetism is taught, modeled, and understood at familiar scales. What makes it especially captivating is how deeply it frustrates intuition. You can keep dividing the material, hoping to uncover a single, lonely pole at last, but the universe keeps answering with a pair. Magnetism seems to insist on balance, no matter how hard you try to split it. Physicists still search for magnetic monopoles in nature. The idea of a magnetic monopole is wonderfully simple and wonderfully disruptive. It would be a particle or object carrying a single magnetic pole on its own, north without south or south without north. Physicists have long been interested in this possibility because such a discovery would deepen our understanding of fundamental physics and help explain why electric charge appears in neat, quantized amounts. Some theories even suggest monopoles could have formed in the early universe under extreme conditions. Yet despite decades of searching in cosmic rays, particle experiments, and unusual materials, no confirmed natural example has been found. That absence makes the search feel almost mythic. Here is a concept that fits beautifully into theory and imagination, yet remains hidden from direct evidence. The hunt continues because the prize would be enormous. Finding a monopole would not be a minor footnote in science. It would reshape one of the most basic stories we tell about magnetism itself. Some exotic materials can imitate monopoles inside their structure. Even though true magnetic monopoles have not been found in nature, physicists have discovered something delightfully strange in certain exotic materials. Inside these systems, collective behavior can create excitations that act in some ways like magnetic monopoles. They are not fundamental isolated poles roaming free through empty space, but within the material they behave as though magnetic charge has separated into distinct moving entities. This happens because the internal arrangement of spins and interactions allows the system to mimic a phenomenon that ordinary magnets never show. What makes this so exciting is that condensed matter physics can sometimes build miniature worlds with rules that echo deeper theoretical ideas. A crystal becomes a stage where impossible-seeming behavior starts to appear in useful form. It is a reminder that nature can be inventive on many levels. Even when the universe refuses to hand us a true monopole outright, matter can still arrange itself in ways that let us glimpse something hauntingly close. The aurora is partly shaped by Earth's magnetic shield. The aurora is not just a light show painted randomly across the sky. Its shape is guided in large part by Earth's magnetic field. Charged particles arriving from space do not simply plunge straight down everywhere. Many are funneled by the planet's magnetic environment toward high latitudes, where they collide with atoms and molecules in the upper atmosphere. Those collisions release light, producing curtains, arcs, ripples, and moving bands that seem to drift like living fabric over the polar night. What makes this so astonishing is the chain of events. Invisible particles race in from the sun. An unseen magnetic structure redirects them. Then the atmosphere answers in color. Green is common, though reds and purples can appear under the right conditions. So when people stand beneath the northern or southern lights and watch them shimmer overhead, they are witnessing a partnership between space weather, atmospheric chemistry, and planetary magnetism. The sky becomes visible proof that Earth is wrapped in an active magnetic world. Earth's magnetosphere helps protect life from charged solar particles. Earth is surrounded by a vast magnetic bubble called the magnetosphere, and it serves as one of the planet's great protective structures. The sun constantly sends out a stream of charged particles known as the solar wind. If those particles struck the atmosphere and surface without restraint, conditions on Earth would be much harsher. Instead, the magnetosphere deflects and redirects much of that flow, steering many particles around the planet, rather than letting them crash directly into it. This is not perfect protection, and some particles still slip in, especially near the poles, but the shielding effect is profound. It helps preserve the atmosphere and reduces the intensity of the solar assault reaching lower levels. What makes this so captivating is that the protection is invisible. We do not wake each morning and see the magnetic shield holding the line. Yet it is there, standing between life and a more violent space environment, quietly shaping the habitability of our world. Solar storms can squeeze Earth's magnetic field like a fist. When the sun erupts with powerful bursts of plasma and magnetic energy, Earth can feel the impact across millions of miles of space. A strong solar storm does not simply brush against the planet and pass politely by. It can compress the day side of Earth's magnetic field, squeezing the magnetosphere inward as though a giant hand had clenched around it. At the same time, the far side is stretched into a long magnetic tail trailing away from the sun. This reshaping can happen on a planetary scale, and it turns Earth's magnetic environment into a dynamic structure rather than a static shell. The image is thrilling because it gives magnetism real physical drama. Our planet is not sitting quietly in empty space. It is being pressed, stretched, and stressed by events on a star far away. When solar activity rises, The magnetic shield responds like a living boundary under pressure, adjusting its form in an ongoing battle with the solar wind. Magnetic storms can disrupt satellites, radio, and power grids. A geomagnetic storm may begin at the sun, but its consequences can ripple through human technology here on Earth. When magnetic disturbances surge through near-Earth space, satellites can suffer communication problems, navigation errors, or increased drag if the upper atmosphere swells. Radio signals can fade or become unreliable, especially at certain frequencies and latitudes. On the ground, changing magnetic fields can induce currents in long conductors, such as power lines, pipelines, and transmission systems. Those extra currents can strain equipment and, in severe cases, contribute to blackouts. What makes this so remarkable is the vulnerability it reveals. Modern civilization feels solid and protected, yet some of its most important systems remain linked to invisible forces extending into space. A solar event can travel across millions of miles and then interfere with the machinery of everyday life, from orbiting infrastructure to electric networks on the surface. Magnetism becomes a reminder that technology still lives inside nature, not outside it. Moon rocks reveal that the moon once had stronger magnetism. The moon today has no global magnetic field like Earth's, which makes it easy to imagine it as a world that was always magnetically quiet. Moon rocks tell a different story. Some samples brought back by astronauts and robotic missions carry remanent magnetization, meaning they preserved evidence that they formed in a stronger magnetic environment than the moon has now. This suggests that in its distant past, the moon may once have had a dynamo of its own, driven by motions within its interior. That possibility changes the character of the moon completely. It stops being a simple dead companion and becomes a world with a more dynamic youth. Ancient lunar rock becomes a message from that earlier age, preserving a memory of a vanished magnetic era. There is something deeply moving about that. A silent grey world hanging in our sky may once have possessed an active internal engine, and the proof survived in stone for billions of years. Mars lost its global magnetic shield long ago. Mars offers one of the most haunting magnetic stories in the solar system. Today it lacks a strong global magnetic field like Earth's, yet parts of its ancient crust are magnetized, showing that the planet once had a more active magnetic past. At some point, the dynamo in its interior faded or shut down, and with that loss, Mars also lost a major protective shield against the solar wind. Over immense spans of time, that may have helped the planet lose much of its atmosphere, contributing to the cold, dry world we see now. The idea is gripping because it turns magnetism into a planetary turning point. A hidden change deep inside the planet may have influenced whether surface conditions remained friendlier or became far harsher. Mars then becomes more than a red desert. It becomes a lesson in planetary fate. Lose the shield, and the future of a world may shift in ways written across billions of years. Jupiter's magnetic field is immense and astonishingly powerful. Jupiter does almost everything on a grand scale, and its magnetic field is no exception. It is vastly stronger than Earth's, and extends so far into space that the region it controls is enormous beyond ordinary intuition. If Jupiter's magnetic environment were visible from Earth, it would appear astonishingly large in the sky, despite the planet's great distance. This gigantic field traps charged particles, shapes fierce radiation belts, and interacts with the solar wind in ways that make the Jovian system feel like a miniature space empire. The source lies deep within the planet, likely connected to layers of electrically conducting material under immense pressure. What makes Jupiter's magnetism so thrilling is not only its power, but its scale. Magnetism there stops feeling like a local property of a world and starts feeling like a space environment in its own right. Around Jupiter, invisible force stretches outward with planetary ambition, dominating vast volumes of space around the giant planet. Some of Saturn's moons move through magnetic environments like laboratories. Around Saturn, certain moons travel through a magnetic setting so rich and varied that scientists can treat the system like a natural laboratory. As moons orbit within or near Saturn's magnetosphere, they interact with streams of charged particles, magnetic fields, and surrounding plasma. Some become electrically linked to the planet's environment. Others disturb the flow around them, creating wakes and patterns that reveal how matter and magnetism influence one another in space. Enceladus is especially fascinating because its plumes feed material into Saturn's magnetospheric system, turning a small icy moon into an active participant in a much larger magnetic drama. What makes this so compelling is the sense of connection. These are not isolated worlds drifting quietly in emptiness. They are immersed in an invisible medium that carries energy, particles, and information. Saturn's moons become experiments that nature is running for us, showing how magnetic environments can shape and respond to bodies moving through them. The Sun's magnetism twists, tangles, and flips on a cycle. The Sun's magnetic field is not calm, symmetrical, or permanently fixed. It is wound and distorted by the star's rotating, churning plasma, which causes magnetic lines of influence to stretch, twist, tangle, and reconnect in ever-changing patterns. Over time, this activity follows a roughly 11-year solar cycle, during which sunspot numbers rise and fall. Across a full magnetic cycle, the Sun's overall polarity flips, and then later flips back again. That means the star's magnetic personality is rhythmic, restless, and self-reversing. This is one of the great reasons solar magnetism is so captivating. The Sun is not merely shining steadily above us. Beneath that steady appearance lies an engine of magnetic complexity changing over years and decades. Those changes matter because they influence space, whether throughout the solar system. Our star does not simply emit light and heat. It also lives through repeating magnetic moods, and those moods can reach all the way to Earth. Sunspots are dark scars caused by intense magnetic activity. Sunspots look like blemishes on the face of the Sun, dark patches interrupting the brilliant surface. They are not holes, and they are not truly dark in an absolute sense. They appear dark because they are cooler than the surrounding solar surface, and that cooling happens because intense magnetic fields in those regions interfere with the normal upward flow of hot material. What makes sunspots so fascinating is that they are visible signs of magnetic stress on a star. They show us places where the Sun's invisible field has become strong and concentrated enough to change the appearance of the surface itself. For centuries, people tracked these spots to learn about solar behavior, long before the full magnetic story was understood. Today, they remain among the clearest signs that the Sun is a magnetic machine. A sunspot is like a visible wrinkle produced by hidden forces below, reminding us that even the bright face of a star can be shaped by magnetism. Magnetic reconnection can unleash sudden explosions in space plasma. In space, magnetic fields do not always stay neatly arranged. Sometimes they are pushed together in ways that build tension. And when the configuration suddenly changes, enormous energy can be released in a process called magnetic reconnection. Field lines are not literal strings snapping, but the effect can feel almost like that. Stored magnetic energy is converted into heat, light, and violent particle motion. This happens in the Sun's atmosphere, in Earth's magnetic environment, and in other plasma-rich regions across space. It helps drive solar flares and other sudden outbursts that can race outward with astonishing force. What makes reconnection so thrilling is that it turns invisible structure into explosive action. A magnetic arrangement can sit there quietly, growing strained. and then transform in moments into a burst of energy large enough to affect whole planetary environments. Magnetism is not only steady guidance and hidden order. Sometimes it is the trigger for sudden cosmic violence. Cosmic magnetism stretches across galaxies, though we barely understand it. Magnetism is not confined to planets, stars, and laboratory devices. It also threads through entire galaxies, shaping the motion of charged particles across distances so vast that human intuition begins to fail. Radio observations reveal that galactic magnetic fields exist on enormous scales, often tracing spiral arms and extending into halos far above galactic disks. These fields seem to influence cosmic rays, interstellar gas, and perhaps even the birth of stars in subtle ways. Yet for all we know, much remains mysterious. Scientists are still working to understand how such immense magnetic structures arise, how they are maintained, and how they interact with turbulence, gravity, and galactic rotation over deep time. That uncertainty makes the subject even more fascinating. We are not looking at a sole chapter of physics, but at a living frontier. Entire galaxies may be shaped in part by invisible force, and we are still learning how to read that hidden architecture across the universe. Even empty space can carry magnetic structure on enormous scales. When people imagine space, they often picture emptiness as blank and inactive. In reality, space can be permeated by magnetic structure, especially where thin plasma drifts between stars or galaxies. A region may look empty to human eyes, yet charged particles moving through it can carry and shape magnetic fields over astonishing distances. This means the space between obvious objects is not always a void in the simple sense. It can be a stage for invisible patterns, tension, turbulence, and energy transfer. Magnetic influence can stretch through tenuous cosmic matter, giving vast regions a kind of hidden organization. That idea changes the emotional feel of the universe. Darkness is not always absence. It may contain structures too subtle for sight, but powerful enough to guide particles and shape astrophysical events. The cosmos is therefore richer than it first appears. Even where almost nothing seems to be present, magnetism can still be there, writing faint but immense patterns through the dark. Ancient pottery can record the magnetic field from its firing day. When ancient pottery was heated in a kiln, tiny magnetic minerals within the clay could align with Earth's magnetic field. As the vessel cooled, that alignment became locked in place, preserving a magnetic signature from the moment of firing. Centuries or even millennia later, scientists can measure that remnant magnetism and learn something about the strength and direction of the field at the time the pottery was made. This is extraordinary because it turns everyday human objects into geophysical witnesses. A cooking pot, storage jar, or ceremonial vessel may carry hidden information not just about the culture that shaped it, but about the planet itself on a particular day in the distant past. Archaeology and magnetism meet inside baked clay. The kiln did more than harden the object. It helped create a physical record of Earth's invisible environment. An ancient pot can therefore speak in two voices at once, telling a human story and a planetary one. Archaeologists use magnetism to find buried walls, hearths, and roads. Long before a shovel touches the ground, archaeologists can sometimes detect hidden structures by measuring subtle magnetic differences beneath the surface. Burned hearths, ditches, brick walls, roads, and disturbed soil can all produce patterns that stand out from the surrounding earth. Instruments moved across a field record these small variations, allowing researchers to map what lies below without digging everything up. It is one of the most elegant uses of magnetism because it turns invisible traces into a picture of lost human activity. A quiet meadow may conceal an old settlement. An empty field may hold the outline of vanished streets. The magnetic survey reveals hints of that buried world with remarkable sensitivity. What makes this so compelling is the gentleness of the method. Rather than breaking the site open at once, archaeologists can listen first. Magnetism becomes a way of asking the landscape what it remembers, and sometimes the ground answers with the ghost of a forgotten place. The black sand on some beaches is strongly magnetic. On certain beaches, especially near volcanic regions, the dark sand contains minerals such as magnetite that respond strikingly to a magnet. Sweep one across the surface and black grains can leap upward or gather into rippling patterns that look almost alive. It is a wonderful moment because the beach suddenly stops being passive scenery and becomes a demonstration of geology in action. Those grains are not merely pretty or unusual. They are fragments of mineral history, often linked to volcanic rock, erosion, and the sorting action of waves. The shoreline has concentrated them into visible patches where magnetism can reveal itself at human scale. What makes this so delightful is the setting. We expect magnetism in workshops, labs, and machines. We do not always expect it under our feet beside the sea. Yet there it is, hiding among the sand, waiting for a magnet to expose a secret written by fire, rock, and surf. Some meteorites carry magnetic clues from the early solar system. A meteorite can be far more than a rock from space. In some cases, it preserves magnetic information from the early solar system, locked into minerals that formed under ancient conditions. By studying that record, scientists can investigate the magnetic environments of early asteroids, planetesimals, and other bodies that existed while the solar system was still young and unsettled. This is thrilling because meteorites become fragments of lost worlds, carrying traces of events and structures that no telescope can now observe directly. A stone that lands on Earth may have begun its story before our planet was fully formed, and inside it may linger evidence of ancient heating, metal motion, or magnetic fields in long-vanished parent bodies. That gives meteorites a rare kind of authority. They are not only visitors from space, they are archival pieces from a deeper age. Magnetism helps unlock their testimony, letting small fallen stones illuminate the early architecture of our cosmic neighborhood. Magnets helped reveal the hidden symmetry inside quantum particles. At the quantum scale, particles carry a property called spin, which gives them magnetic behavior even though they are not literally spinning like tiny balls. This magnetic character became one of the clues that helped physicists uncover deep symmetries and hidden structure in the quantum world. Experiments involving magnetic fields showed that particles can align in discrete ways, split into distinct states, and respond with a precision that classical intuition never predicted. Those results helped build the foundations of quantum mechanics and transformed our picture of matter. What makes this so astonishing is that an ordinary-seeming idea from magnetism opened a door into one of the strangest realms in science. The magnetic response of particles revealed that nature at small scales is quantized, structured, and far less continuous than people once believed. A field applied in a lab could expose hidden order in reality itself. Magnetism became not only a practical force, but a guide to the secret grammar of the quantum world. Future computers may store information by spinning tiny magnetic states. One of the most exciting frontiers in magnetism involves spintromics, a field that aims to use the magnetic character of electrons, especially their spin, to process and store information in new ways. Conventional electronics mostly rely on the movement of charge. Spintronics asks whether devices can also exploit the orientation of tiny magnetic states, potentially making memory faster, more efficient, and less power-hungry. Some modern technologies already use related ideas, and future advances could push them much further. What makes this so captivating is the scale of the ambition. Engineers are trying to build tomorrow's information systems by controlling magnetic behavior at levels almost too small to imagine. The humble magnet on a desk and the future of computing may seem worlds apart, yet the connection is real. Invisible states inside materials could become the basis of machines that remember and calculate in ways unlike today's devices. Magnetism may help shape the next great leap in information technology. Magnetism is everywhere, yet humans cannot see it directly. Perhaps the strangest thing about magnetism is how present it is, despite remaining invisible to human sight. It guides compasses, shapes auroras, runs motors, stores data, influences animals, and stretches through planets, stars, and galaxies. Yet none of that appears directly to our eyes. We see only the effects. A needle turns. Iron filings arrange themselves. A speaker vibrates. A medical scanner reveals hidden anatomy. The force itself remains unseen. That gap between presence and perception is part of what makes magnetism so enchanting. It surrounds daily life and cosmic space alike, but it has to announce itself indirectly through motion, pattern, light, or technology. Humans learn to detect it by building instruments, devising experiments, and noticing clues in the behavior of matter. In that sense, magnetism is a perfect scientific subject. It reminds us that reality is larger than our senses alone. The world is full of structure we do not naturally perceive, yet can still come to understand. As our journey through magnetism comes to a close, we can leave with a strange and comforting thought. All around us, the world is full of forces we never see. Tonight, we drifted from the deep iron motions inside Earth to the glowing curtains of the aurora. We followed birds across the sky, turtles across the sea, and tiny bacteria through hidden watery worlds. We passed through hospitals, power stations, scrapyards, kitchens, train lines, and distant planets, and everywhere magnetism was there, shaping motion, memory, direction, and light. It has been, living in compass needles and sunspots, in black beach sand and ancient pottery, in the moon's lost history and Jupiter's enormous reach. It has helped us look into the human body, build modern machines, and glimpse the hidden order inside matter itself. What began as a simple pull between metal objects opened into something much larger, the force that threads through daily life and out into the dark between worlds. And now, as this unseen universe grows quiet around you, there is nothing more you need to hold on to. Let all those images soften. Let the glowing skies, the drifting particles, the turning planets, and the silent fields fade into the background. Let your breathing slow. Let your thoughts loosen their grip and settle gently into stillness. Thank you for spending this time here with me. If you enjoyed this journey, perhaps leave a like, subscribe, or share a thought below. And if you happen to still be awake in a moment, there will be another video waiting for you on the screen. For now, you can simply rest and let the invisible world keep turning without you for a little while. Sleep well, and good night.